Water is the most precious substance on Earth and a primary building block of life. Humans can't live more than a few days without it. Yet, in order to grow, cultivate, process, and transport our food, we waste a tremendous amount of it. So much so that we need to pull more of it out of the ground just to satisfy our agricultural needs, making matters worse. A report in the June 2023 issue of Geophysical Research Letters indicates that depletion of groundwater was a significant contributor to sea level and climate change. The majority of the southwestern United States, northern Australia, most of the South American continent, all of North Africa and the Middle East, and parts of Western Asia are in perennial drought. We need water to live. Yet we also need water to make the food we rely on to live. And we never seem to have enough of it. Why the trade-off? Why so much waste? Is there a way to reduce our consumption of water with integrated circuits and AI? How could microchip technology help conserve our most precious resource? Let's go beyond the microchip and hear a story of empowering innovation to enhance the human experience. Returning to the podcast. This is your third time, guys. Returning to the podcast are Ross Satchel and Toby Sinkinson. Ross and Toby are applications engineers at Microchip Technology working out of the 8-bit microcontroller business unit. They join us again today from our global headquarters in Chandler, Arizona. Welcome back, guys. A three-peat.
Thanks,
thank
Dana.
you.
In the intro, we briefly talked about the problem around how we use water in agriculture and the need for new methods of conservation. I'm sure we're just barely scratching the surface of this problem. How deep does this go? And what can you tell us about it?
Well, fresh water is always, in our lifetimes, always increasing in scarcity. And we're already seeing droughts exacerbated by the effects of climate change. And we can expect to see these knock-on effects accelerating in both intensity and in frequency. And so the symptoms of that are longer droughts. And then you end up with also more frequent and heavy precipitation and floods, and wildfires, and outbreaks of invasive pests. And this means that for agriculture, it results in lower farm yields, also means a greater or increased susceptibility to these invasive plants and pests, as they're outcompeting all the natural animals and plants. And then also we're seeing saltwater intrusion on coastal areas and also changes to the ecosystem structure. And so it means that the animals and plants that are most able to adapt will succeed, because that's the whole driving force of evolution, right? The one that is able to adapt most rapidly is the one that succeeds. And this means that typically pests are the ones that are able to adapt, and they will wipe out our native species.
You know, I would add to that that, you know, growing things here in Arizona versus growing in California or growing in the Midwest, they all have like different systems that you're working with. I think when we're talking about our microcontroller parts and our sensors, being able to make our design fit where we're growing is a huge advantage, because what works here is not going to be the same. Like I think we mentioned in an earlier episode, we've worked with a farmer who does flood irrigation. That's not something you have naturally in California. That's a different design. So,
Right. The classic lawn sprinklers from the football field versus a drip irrigation system. There's levels of water depending on the soil, but in general, we think we probably use too much of it, right?
Absolutely.
yeah, overwatering is usually the best option when it comes to growing. We talked about that also earlier. Underwatering is much harder. But I think in our culture, we, like you said, leaving the sprinkler on or whatever, it is definitely this area where we see people taking for granted how lucky we are to have this abundant resource here in the U.S. in particular, or in places of the U.S. In other parts of the world, they don't have, like you mentioned earlier, they don't have that luxury, right?
Right, and there are pretty serious problems here with far-reaching implications, but it can't all be doom and gloom, can it? I mean, what methods are we using now to try and conserve?
Well, I just want to start with the farms in the southwest United States actually only comprise about 8% of all the cropland in the United States, to the value of around about $34.5 billion per year. And agricultural water use of that accounts for 78% of all water withdrawals in the region. So it's almost the vast majority of it is agricultural use. And
I mean, we're not talking about showers and doing the laundry, right? This is farmland.
Yeah. And so the idea of overwatering being better than underwatering, which it is, but if you can get the optimal amount of water to where you need it, then that is the best case scenario. So you can both optimize your yields and also minimize your water consumption for that level of yield.
What are some examples of saving water? We talked a little bit about vertical farming. I'm particularly interested in something you said earlier regarding, was it white ceilings or white roofs?
White roofs.
Can you go into that?
Sure. So there's green roofs and white roofs.
Okay.
And so the idea is white roofs is you simply paint the roof of a building white. And so it reflects most of the light. So it means your air conditioning requirements are reduced. And it sounds like it's straight off the bat, it sounds like it's a really good idea. But there's some evidence that's starting to mount that suggests that it reduces the vertical transport of moisture. And this results in reducing cloud formation, and then you end up with less rain. Now, we need a lot more evidence to determine whether or not this is in fact what's happening. But the alternative to that is doing green roofing. So you get the dual use. So you can produce food on your roof, and you can also reduce your cooling requirements. And because you're growing food there's a vertical transport of moisture from the evapotranspiration from plants. And so hopefully that will deal with the problem of reducing cloud formation and help increase humidity and therefore cloud formation and end up with more rain.
I love that story. It's a little bit tangent here, but there's some hotel in Silicon Valley, right? That's like they're trying to set up the hotel to entirely operate off of rainwater that collects by circulating the water in the building. It's pretty remarkable, and I think we'll see more of that kind of innovation all over. And it certainly could apply on the farm. The kinds of water that you're using and reclaiming, gray water and all kinds of things like that. Maybe cities' gray water somehow is used. I'm not sure, what that looks like.
I did see something about gray water reclamation in San Francisco. As far as a hotel using all the rainwater to be completely sustainable, I would have pictured Seattle instead of San Francisco, but I guess we'll take what we can get. With regards to gray water, we're talking about any kind of water.
Well, it's like shower water or water from doing the dishes, but it's not black water. That is toilet water.
Okay.
Generally, that goes down the sewer and needs to be treated.
And that's a no-no.
However, there is, particularly in Australia, there's been a lot of usage and reclaimed and recycled water increasing in popularity, mostly for non-drinking purposes. So there's a town west of where I grew up, and the town is called Toowoomba in the state of Queensland. And it's a largely rural agricultural community. And because they were having such problems with drought, they started doing reclaimed or recycled water. But there's still the mental block for most people of drinking water that has been reclaimed or recycled. Even though that water has been fully treated and it's perfectly safe to drink, it's kind of like on the same level as eating insects. Most of us go, yeah, that's probably something that we should be doing, but can I just pick up this grasshopper and eat it? It's like, oh, yeah. So there's definitely a mental block there with regards to that. But so a perspective. So I'm Australian, and Australia is the driest inhabited continent on the planet. So Antarctica is the driest, but considering the population of it is like under. So I think it's under 1,000 people, and none of those people are permanent residents.
We would
so
label it habitable, right?
Exactly. So when I first moved to the United States in 2008, it blew my mind. I was living in New York City first, and it blew my mind that the water waste. So it's like someone in the local community would have a key to the fire hydrant, and there'd be a basketball court nearby, and for people to have access to water while they're playing basketball, they would just turn the fire hydrant on, and it would be just gushing down the street. And I was horrified. When I left Australia, we were in level 3 water restrictions out of 5. So you could only water your lawn one day a week between particular hours. If you wanted to wash your car, you had to use 2 buckets, 1 bucket of soapy water, 1 bucket of fresh water to rinse it off, and that was it. And because we're so dry, people take it very seriously and will report their neighbours if their neighbours are wasting water, because we don't have much of it. But we do have about 270 desalination plants. Now, most of these are pretty small, but the largest plants, like there's one on the west coast near Perth, that can produce about 70 million gallons per day. Now, that might not sound like a lot, but when you realise the population of Perth is about 1 million people, that's actually a huge amount of water, because it means each person could potentially use 70 gallons a day, which is a lot of water. And so
Your average water heater for a family of 4 is 50 gallons.
there you go. So you could do that 5 times and a little bit left over. Because one thing that a lot of people don't realize is that about half of 1% of all water on Earth is actually available fresh water. There's 3% total, but 2.5% is locked up in glaciers, polar caps, the atmosphere, and the soil. And so that leaves us just half of 1% that's actually available to us of all of the water covering the 70% of the planet.
Counterintuitive when you look at a picture of the globe, right?
Right.
So in terms of smart ag and integrated circuit technology, where are some ways we can leverage microchip technology for water conservation?
Well, one of the big parts of it is applying the water to your farm where it actually needs it. And so by measuring the soil moisture, and we think possibly even the soil temperature, which looks like it's a close correlation for it. We're still experimenting with that. But by determining where you actually need the water and applying it there, so you selectively water your farm. So that reduces the amount of water that you're consuming, which means there's more available, leaving that in the aquifer rather than pulling it all out of the aquifer and then just creating these knock-on problems like kicking the can down the road until we eventually run out of water.
We use sensors. Any particular type of sensor for water conservation or general purpose like we've been talking about?
Well, yeah, the soil moisture sensors are definitely what we've had a lot of focus on. And, in that light too, the depth that you're measuring becomes very important. Like, are you close to the root system? Do you need to be below it? Do you need, or knowing what's near the ground level? But yeah, and Ross mentioned there that it may turn out that a soil temperature sensor might work. There's also some pretty innovative ideas out there. We've looked at things like doing like an RFID sensor where, just like the capacitive trace, where we could have something pass over it and go down and read that RFID image and then use that to calculate the dielectric. Same kind of principle as we're doing with the capacitor here, trace, and be able to gauge that. Again, it's what we're going after there is how do you do this without disturbing the soil? Like every time you move the soil or like it gets compacted, these readings are less reliable. And so, or need to be recalibrated. So that's an interesting piece there. It's like I said, I think earlier episode, the soil is like the final frontier. There's a lot to learn still about, particularly around the moisture there and how it relates to growing things.
Something I want to add to what Toby was saying about placing moisture sensors at different levels, because a lot of plants have a root ball or a root zone that's less than 1 foot or 30 centimeters deep. So if you're able to place these soil moisture sensors at different depths, you can actually see how much of the water you're putting into the soil is being absorbed by the root zone and how much is actually just going further down. I mean, sure, it's helping recharge the aquifer, but if you're already low in water, you really want to minimize the amount that you're using. So if you can just use the amount that's absorbed by the root zone, that's probably the optimal case.
Yeah, that's a great point.
What about vertical farming?
I think vertical farming has great applications, particularly in city areas. So you can solve several problems at once. One is that you can do high density farming, since it's not all just flat, 1 or 2 dimensional. You can make a 3-dimensional farm. It's only really applicable to certain crops, like things like carrots, for example, probably wouldn't do so well. But your leafy greens and things like that are probably the ideal use case. And one of the things you can do is one of the things in hydroponics is usually a run-to-waste system, which is very water-intensive because you're just throwing the water away along with the nutrients. So if you're able to measure not just the pH of the solution, not just the total dissolved solids, but the individual nitrogen, potassium, and phosphorus, and tweak this recirculating solution so that you can keep using that over and over again. So the only water really that you're losing is through evapotranspiration from the plants themselves. There's some issues with if you get rain, does that dilute the system that you have? And sure, probably the answer is yes. But if you're recirculating this and measuring all of this, you can just keep adjusting your solution and you can automate this entire thing. So that way you just have a dashboard and you can see what's going on.
You gave us a recipe in one of our earlier episodes together about was it a homemade fertilizer?
Kind of. It's quite popular in people that do some kind of home farming in a non-biological medium. So, like for example, vermiculite and perlite is a popular one, and you can just use worm castings. So you start off with fresh water, and then you put a air stone in it and just bubble it for a while. And the idea of that is there's a certain amount of chlorine that's used to treat our water, and it's not good for these beneficial bacteria that we want to introduce to it. So usually you bubble the water for at least 24 hours, then it helps boil off the chlorine. Then once you've done that, you then add worm castings to it. And there's lots of little microbes and beneficial bacteria in that. And by continuing to bubble it, you're helping them really colonize that water. And then you can add things like bat guano. And there's some issues with bat guano because often it's mined from caves, which then causes ecological problems of its own. But then you can also add things like liquid kelp and a bit of blackstrap molasses, and you have this worm castings tea, basically. And then you just measure the concentration of the solution and dilute it to whatever you need for the plants that you're putting it on. And you can apply it to the root zone, but you can also apply it in a spray form to the like a foliage spray to the plants themselves.
And I remember you saying that overwatering can affect the taste. I think you talked specifically about watermelon.
Oh yeah, it's how much because we were talking about how the underwatering causes the crop to fail or not produce the yield that you need. But then you want to you compensate by overwatering. But then there's some sort of happy middle ground there where instead of having a watery flavor, you've condensed the nutrients and the flavor down. So there's a sweet spot there that if you can arrive at, then what you've done tastes better. It costs less to produce. You've used less water. You were just reminding me too, and I think I mentioned earlier today to you, but another thing related to that mixture, we used to experiment. There was an idea, I think it was developed in Hawaii, where they were using, they kind of had limited resources for composting. And so this method called the bokashi method was developed where you basically, it's an anaerobic, I believe, process initially where you place your food waste, and it can even have things like cheese and meats in there that normally you can't do, but you layer this like mixture of molasses and wheat germ and these microbes, and you layer it up and you let it sit for 2 weeks, and then you have to pour off the tea. I remember using this stuff. You could pour it down the drain, and like your drains had never run more cleanly as they ever did. But then you dump that into another a place where it can sit for a couple of months, like under soil, and then it's more like your traditional compost. But I think there's like lots of these alternative like ways that even in urban environments. So that's what we were forced into doing. Is we were in an urban environment. We don't have a place to compost things. There's a lot of great solutions. I realize that's not really back to our integrated circuits anymore, but that did remind me.
Well, part of that is also monitoring the solution that you're creating and saying, do I have say my NPK or nitrogen, phosphorus, potassium? These are the needs that I have, and adjusting your solution and then diluting to whatever it is that you need to feed the crops that you have.
Right. One thing to have the compost, but is it the right compost in the right amounts?
Yeah, because I remember too, if you dump this onto plants, like you said, you can use it as a fertilizer, even the leaves and stuff, but you want to be careful because if that pH is too acidic, you could do a lot of harm. So having a way to like measure that as you're going would be great. Yeah.
So what kind of devices are we looking at for water conservation? I would assume sensors from our catalog. Do microcontrollers get involved? What technology are we looking at for water conservation?
So there's a whole, in terms of soil moisture, there's a whole range of different types of sensors that you can use. And there's anything from a really low-cost resistive sensor, which are problematic because they tend to corrode. Although if you use one with what's known as a relaxation oscillator, it can last for significantly longer and prevents the corrosion of one of the ends of that. However, they still break down in time. So the next step up from that is a capacitive sensor, and you drive that with a pulse train, and then you have some DC smoothing circuitry at the end of it, which is it's basically just a capacitor, it's a diode and then a RC filter, basically a low-pass filter to smooth that out, and you can directly read the analog value off that, and it requires some calibration. Next step up from that is what's called frequency domain reflectometry, and that's sort of getting into RF territory, and it approaches, it's a fairly low-cost method, but it approaches what is basically the gold standard of soil moisture sensing, which is time domain reflectometry. And the concept is, this actually came about for measuring where, say you have a coaxial cable and there's a break in the coaxial cable somewhere, but you don't know where. So you send this pulse down the cable, and because you know the speed or the velocity that the pulse moves down, it will bounce back. And because you know that velocity, you can actually convert that into a distance. And then you can say, I know that the break is here, so we'll chop out this section of cable and then splice in some replacement cable.
Even if that's like several kilometers under the ocean, like
Absolutely.
that, I think that's
Wow.
just kind of where you can't get out there to test it, right? This is some of the reason.
And so then what they've done for soil moisturing is they say, okay, well, we have these two probes. Instead of the distance being unknown, we know the distance. The one thing we don't know is the effect of the medium that it's traveling through. And depending on the density and water content of that medium, that will change the speed that it then travels through. And then you can back calculate the moisture in that. So it's quite very, very clever, but it's quite expensive. So often people will either go a capacitive sensor or a frequency domain reflectometer.
And we're talking again about feature and price differences, right?
Yeah, 4
Absolutely.
orders of magnitude at least, like from like cents on the dollar to thousands of dollars.
Well, it's nice to have options.
But these technologies really haven't changed a whole lot in the last like decades. Like this is still very ripe for innovation. And yeah, that's why that's why it's so fun to be working on some of these problems. And it might be like we've heard some pretty out there ideas recently about other ways that this might happen too.
So suppose one of our listeners has a use case for this technology. Where could we send them? How would they adopt it?
So I would recommend that they start at Toby's Hackster article that came out of his capstone project. And if you go to hackster.io and use the search term agricultural IoT, and then just search for just look for the article that was written by Toby Sinkinson.
Okay, we'll make sure we put that link in our show notes for anybody that wants to follow along. You just kind of hinted at it, Toby. What are the implications of this technology? Do you have any predictions on the future of where we're going? How will we be saving water tomorrow and in the years to come? And what are some possibilities that the technology will allow for? What breakthroughs could we possibly be looking at?
Yeah, I don't know. I think I've always been one of those like optimists, and this is an area that's like, it feels like every day we hear some other statistic or some other really discouraging fact that comes our way. I think I've always found it so fun to work on and work on stuff like this where what we need is right here, so I'm very hopeful. I think like just discovering like in our own process here that we could come up with something that pretty relatively inexpensive to do that was able to capture a more accurate reading here. It's just thrilling. So I think, going back to, I think it was our last episode, we were talking about these like high-tech devices that are harvesting. I think the same kinds of stuff can go into water conservation, and that this is, when you hear those discouraging facts about water, like, that this is going to be an area that we need. And I hopefully that people can grow more grateful and more better stewards of what our resources that we do have.
Ross, what do you think the future holds?
It's both scary and exciting because it's a great time to be an engineer because we love to solve problems and we can see a lot of problems. So it gives us so many opportunities to do things and benefit humanity. Ultimately, I think it is a very exciting time to be alive because we can actually do something really useful with our skill set.
Well, I know that Microchip is using our technology in the realm of sustainability in general. And sustainability, loosely defined, is the reduction of resources. So how can we use less water? How can we use less power? How can we generally be sipping, I think is the term you've used in the past. What is it about our products that you think can help us with sustainability goals in general? Water conservation obviously is the top of our list, but are there other areas of sustainability where we're making an impact? Absolutely.
So we've been seeing just with the rise of Internet of Things, it's enabled us to do basically quantified self. That was a movement in Silicon Valley when I lived there about 10 years ago. The idea was just tracking all this personal data, but it's not just personal data like your health and fitness, but it's things like improving transportation, like public transport, for example, sequencing traffic lights in such a way to reduce pollution and optimize the traffic. There's things like smart homes. So the idea is that when you leave home in the morning, it adjusts the air conditioning so it's using far less power, but it's still optimized in such a way that when you're about to return home, it uses the minimal amount of power to get to a comfortable temperature. So all of these things, like it's quite incredible the massive rate that, or the incredible rate that we've seen this technology change everything around us. And it's even things like the supply chain. So like tracking the temperature of a carton of milk as it goes from the creamery to your local store and enables the whole supply chain logistics to optimize their processes because they might see at a certain point in the travel of this one carton of milk that the temperature goes outside of its optimal range, and then they know where they need to deal with it so they can make sure that that carton of milk achieves its specified lifespan according to the use-by date.
Any final thoughts?
Yeah, that reminds me too, just like, these different systems or commerce is driven on one aspect here, and that has some very rigid or well thought out of parameters there. I think with the collecting the kinds of data that we're able to come up with, we help, and farmers have always worked with this, but we help see beyond the immediate system and start seeing the wider systems that are involved, to be able to pull that in to make better informed decisions. I mean, a lot of those issues that we're talking about are where things are kind of just outside the boundary, or it depends on where you frame it. So that's fun to be able to find a way to incorporate more of a wider ecosystem into what we're doing.
That leads into as well, there's two main types of machine learning, and one is supervised and the other is unsupervised. So supervised is you have all of these inputs and you're measuring those and you're quantifying them, and at the end you say, this is an acceptable result or it's not. And then there's unsupervised, where you just feed this thing a whole lot of data and it goes through and it finds patterns in the data that a human could never find and normal machine learning algorithms can't find either. And we're already using deep learning to find all sorts of weird and wonderful patterns in things that are enabling us to optimize all sorts of things. It's an amazing time to be alive.
I think that's a great place to end it. Ross Satchel and Toby Sinkinson are application engineers at Microchip Technology, working out of the 8-bit microcontroller business unit. They join us again today from our global headquarters in Chandler, Arizona. Guys, thanks for joining us.
Thanks for having us, Dana.
Thank you for venturing beyond the microchip with us. Join us next time as we continue to explore empowering innovation to enhance the human experience.